So how do we use a mathematical model and tie it into a theory? So I want to do a few examples with you here. So in example one, I have voltage and current. You haven't learned about that yet, but it doesn't even matter. You don't have to know anything about it in order to answer these questions. What we're looking at is, this is the equation of the line. And if you don't recall how to generate the mathematical model, you should go watch the videos on how to make a mathematical model. But so I have here the mathematical model. The voltage is equal to 989 times the current, which is on the x. If you look at your equation sheet and look at your notes and the videos you've watched, right, on the content that we've covered in class, so in this case, this would be about electricity. You want to look at, well, what equation has voltage and current in it? And then you'll find V equals IR. You'll find that on your equation sheet or some form of that. And so if you know that V is on the Y and I is on the X, then you know that 989 must be this R, whatever R means, right? And you don't know what R means right now, but that's how you use the mathematical model and tie it to the theory. So the theory here is mirrored by the results of your lab experiment. Here's another example. Y equals 4.7 x squared. This is a distance time graph. Here's your mathematical model. D equals 4.7 t squared. If you, again, you want to look on your equation sheet, look in your notes, do some reading. You know, this is kinematics. And what equation has D equals something times t squared? And you may recognize our kinematics equation, VOT plus 1/2 AT squared equals displacement. So what do you use this for? Well, now you can kind of say, okay, what happened to this whole term is VOT. Well, there must have been initial velocity 0 or close to 0, right? Because my y-intercept is 0. So if that's true, and this is D is on the y, and t is squared and it's on the x, then 1/2 acceleration must be this 4.7. And it's another way to interpret the results of your graph, because that everything has a meaning, right? You're using this theory. Now we're doing this backwards, right? When people were discovering this stuff, they made the graph and then developed the equation. We get to do it the other way around. We're validating equations. So we have the theory, and now we can tie that tightly and say, look, we just confirmed that this equation is true because our mathematical model reflects the theory. All right, last example. This is acceleration versus mass. So we've got y equals 1.6 x to the -1. So the -1 power means inverse. And so this can be rewritten a equals 1.6 over m. Well, what equation has acceleration and mass in it? Well, that's force equals mass times acceleration. That's Newton's second law, which again, you may not know yet, and that's okay. But if you look at your equation sheet, you'll find an equation that has mass and acceleration in it. But the thing is, it doesn't have acceleration on the left side of the equation, but we can rearrange the equation to get it in that form. If you rearrange it, you get A equals F over M, and you can see A is here, M is in the denominator, so the force must be 1.6. So these are just three examples of how you can use theory and the mathematical model to create your reasoning statements.